In this video, we're going to look at how groups that are already on our benzene ring will affect the reactivity of that in electrophilic aromatic substitution reactions. So there's two different effects we're going to look at. We're going to look at inductive and resonance. So first, with inductive effects, the way you really want to think about this is based on electronegativity. So a couple examples, we can have halogens attached to our benzene ring. So something like chlorine. We could have acyl groups. So something like a ketone or an aldehyde. Another one to think about would be a nitro group. I'm going to draw that nitro group out because it helps to see what it looks like when thinking about this. Another common example would be a hydroxyl group. And then one more we will look at will be just an alkyl group, so something like a methyl. So to think about the inductive effects, we want to think about the electronegativity of these groups. So chlorine is electronegative. It's going to pull the electron density towards it, making it partially negative, and therefore the carbon that it's attached to will be partially positive. With acyl groups, if that carbonyl carbon is directly attached to the benzene ring, there is resonance, making that oxygen partially negative and this carbon region partially positive. Nitro group, we've got resonance that we can pull electrons out. So again, we've got partial positive on the ring. Hydroxyl group, oxygen is electronegative, so again, partial positive on the ring with the negative out on the group. So all of these have kind of that same pattern where the electron density is being pulled out into the group and away from the ring. So we would call these electron withdrawing groups. All that electron density is being pulled out due to electronegativity. With alkyl groups, that alkyl group is actually donating electron density. Our dipole would be pointing into the ring for that bond. So this would be considered electron donating. Because our dipole is porting in. So that's one effect, one way we can think about these effects. Another way to think about this is with resonance. So it aligns very much with the electronegativity in most cases, not in all cases, but with resonance, at least in my opinion, it's easier to see because you can actually move the electrons around to see, are they being pulled out of the ring or being pushed back into the ring. So some generalization here. If you have your benzene ring and some group, I'm just going to call Y as generic. So when Y has a pi bond, and by pi bond I mean the carbon or atom that's attached directly to the benzene has to have the pi bond, then your electrons are going to be pulled out of the ring. So this is electron withdrawing. So electron withdrawing group is kind of the common abbreviation. When Y has a lone pair, those electrons are going to be pushed into the ring. So we're going to call that electron donating. So electron donating group. So that's kind of the quick glance answer now let's look at drawing some of the resonance structures of these groups so we can see how this process occurs. So let's look at a group where the carbon attached has a pi bond. So one very common one would be your acyl group. So again, the carbon that's attached to the benzene ring is part of a pi bond. So what can happen is those electrons in the pi bond can kick up to the oxygen. That now puts a positive charge on that carbon, negative charge on the oxygen. Now I have that empty p orbital on that carbocation, so I can take electrons from the pi system of the benzene ring and kick them out. So notice here I'm now removing electrons from the ring itself. So this is an electron withdrawing group. So now that carbocation is part of the ring. I can keep going. I can continue to draw resonance structures and move that positive charge around the ring. So there's one step. Here would be the next one. All right. One more step and I'm back to where I started. So as you can see, I've removed the electron density from the ring, putting the carbocation on the ring, making that acyl group electron withdrawing. Let's look at one more example here of an electron withdrawing group. Another common one is a nitro group. So that's a carbon triple bonded to a nitrogen. So again, that carbon has a pi bond. So I can kick electrons out to nitrogen, putting the positive charge on carbon and the negative charge out on the nitrogen. Now again, I can pull my pi electrons out of my benzene ring, moving that carbocation into the ring. And again, you can move that carbocation around the ring. So again, now an example of another electron withdrawing group. Let's look at electron donating group. So now if I have something that has a lone pair attached to the benzene ring, like a chlorine or any halogen, that lone pair can be kicked in and the pi electron from the benzene system can pop out as a lone pair. So now you can see electron donation. The electrons are being pulled from the group and put into the ring. Another example, I can have an amine group so that nitrogen has a lone pair. Again, that lone pair can be kicked in. And is considered an electron donating group. So there's several examples. You have your electron withdrawing, where you're putting a positive charge on the ring because you're removing electron density, and electron donating, where you're putting lone pair into the ring. So we've seen both the inductive effects and resonance effects. Like I said, most of the time they are in agreement. However, there are examples where inductive and resonance are kind of going in opposite directions. One example would be the halogens. So with inductive, we said that chlorine is electron withdrawing. Right? That's electronegative. It's pulling electron density out. With the resonance, it's putting electron density in. So when they go in opposite directions, typically resonance wins. The one big exception to that is the halogens, where halogens are considered electron withdrawing, and because the electronegativity inductive effect is stronger. So how does this affect the rates of our reactions? So remember, we're talking about EAS, or electrophilic aromatic substitution, and in these reactions, your benzene is the nucleophile. You're going to have some kind of electrophile, and your pi system is going to attack that electrophile. Remember, good nucleophiles have electron density, negative charge even better. So any ring that has an electron donating group, so that negative charge has been moved into the ring, is going to be a better nucleophile. So anytime you have an electron donating group, that's considered an activator. An electron withdrawing group is a deactivator. Because it's making your your nucleophile positive, which is not what we want. So whenever you've got the electron donating group, it's an activator, an activating group, however you want to say it. The reaction is going to go faster. The rate will be increased. If you have an electron withdrawing group or it's deactivated, it's going to go more slowly. So that's how your groups are going to affect the rates of your reactions. Electron donating groups or activating groups, the reaction will go faster. Electron withdrawing groups or deactivating groups, and the reaction will go slower. Here is a good summary table of these activating and deactivating groups from Mastering Organic Chemistry website. There is a ranking, right? So we've got strongly activating all the way down to strongly deactivating. The exact cutoff is arbitrary, but this gives you a good idea. So if our baseline benzene is right here, any of the groups to the left are our activating groups. Groups to the right are the deactivating groups. And notice that we have groups that have lone pairs directly attached to the ring, plus the alkyl groups. We didn't talk about those except for with the inductive effects. And then we have our groups that have pi bonds. If you draw all of these out, you'll find, at least in most cases, pi bonds or positive charge. Here the haloalkyl, because the fluorine is so electronegative, it's pulling electron density out. The in between place then where we've kind of mentioned is a weird exception are the halogens. So the halogens with resonance are electron donating because they have the lone pair. However, due to the electronegativity being the stronger factor, they are actually deactivating. So there's a little bit of fuzzy line there, right, between what's activating and what's deactivating. Understand the general concept. You can always reference tables like this if you need to, but make sure you can draw those resonance structures to explain why something is either activating or deactivating.